Hello, rockstars. In the last class, we talked about work, energy, and power. In today's class, we will be advancing to another important topic, elasticity. And in this class, we will split the lesson into three different sections. In the first section, we will be talking about the concept of elasticity. Secondly, I will be listing the formulas in elasticity. And thirdly, we will be using those formulas to crush UTME questions. Let's get started. Greetings, future rockstars, and welcome to Josh White Academy, where we fuel your success with experience-backed strategies and science-based tutorials. If you are new to this channel, I am your host, Josh White, and it's my mission to help you crush high school with confidence and clarity. So please do well to hit the subscribe button, turn on the notification. Let's get started. A body is said to be elastic if after being compressed or extended and released, it returns to its original size or length. Now we will be explaining this phenomenon with a law called Hooke's Law. Hooke's Law, it states that the force applied on an elastic material is directly proportional to the extension, provided the elastic limit of a material is not exceeded. If I remove my proportional sign, I will add a constant called K. This constant is called the force constant or the elastic constant, or you can just simply call it stiffness. Hooke's law can also be stated that provided the elastic limit of a material is not exceeded, the stress is directly proportional to the strain. And if we remove our proportional sign, we will add a constant. This constant Y is called the Young's modulus. That's why Young's modulus is equal to stress divided by strain, as we will see subsequently. Now, this law makes us to understand that the more force that is applied on a material, the more the extension. So if I increase the force I am applying on an object, the more the compression or the extension of that material. And likewise, the more stress, the more force I apply to a specific area of the body, the more the body experiences an extension in relation to its original length. Now, we will also be explaining this using a graph that explains the strain of a body, how force relates with extension, or how stress relates with strain. So here is a graph that explains the relationship between force and extension, a graph of force against extension. Now, E here signifies what we call our elastic limit. At this point, Hooke's law, between this point down, Hooke's law is obeyed. That means the more force you add, the more the extension. So the more you are increasing the force, the more the extension is increasing. So at this point, Hooke's law is obeyed. That's why your statement of Hooke's law is not correct unless you add that provided the elastic limit of a material is not exceeded. Because if it is exceeded, Hooke's law no longer holds. So this is the E is the elastic limit. Then we now have the Y. The Y is called the yield point. At this point, that object, even if the force is released, that object will no longer return to its original size or length. The object behaves like a plastic. Little force causes higher or more extension, like that of a plastic. So we call that the yield point. That object is no more elastic. Then we have our M. Our M is the maximum load. Our maximum load reveals the highest level of force that elastic material can bear. If force more than this maximum load is added, the object will experience a B, which is called the breaking point. That elastic material is torn apart. So when a force is applied to an elastic material, the bond between the molecules of that material is stretched but not broken. So even after the force is removed, the object returns to its original length or size. But when that material is stretched beyond its elastic limit, the bond between the molecule becomes broken, but the molecule forms bond with other neighboring molecules. So the object still remains intact but does not return to its original length and size. But when the maximum load or carrying capacity as it regards force is applied to that object, the bond between the molecules completely go apart, causing that object to break. So this is used to explain Hooke's law of how a material obeys Hooke's law and beyond it no longer obeys Hooke's law. Now, the kind of energy that is found in a stretched spring or in an elastic material is a kind of potential energy we call elastic potential energy. Like for instance, a boy stretches a catapult. The energy in that elastic material is called the elastic potential energy, as we will see subsequently. So now let's move to the second section of this class. Let's list the formulas in elasticity. Come with me. As we said the first time, our force is equal to Ke from Hooke's law. Secondly, the elastic potential energy. As I said previously, this is a kind of energy found in a stretched material. So the elastic potential energy is equal to 1 over 2 Fe. Remember, our F is our force, our E is extension, K is the force constant or stiffness or elastic constant. Also, our elastic potential energy is 1 over 2 Ke squared. Remember, our F is Ke, so F is replaced with Ke, it gives you Ke squared. Now, we have what we call stress. Stress is force all over area. Similar to pressure, we have strain. Strain is extension all over length. This one does not have any unit because of extension is measured in meters, length also measured in meters, so meter cancels meter. Then we have our Young's modulus, as we said previously, is stress divided by strain, which will give you FL all over AE. And lastly, in some instances, they may tell you a man shoots a stone from a catapult. So there is a conversion of energy from the energy in a stretched spring called the elastic potential energy into kinetic energy of a propelled stone. So in that case, we will say our elastic potential energy is equal to our kinetic energy, which is 1/2 Ke square, or 1/2 Fe is equals to 1/2 mv square. So these are the formulas you need to crush any questions on elasticity. Now, can we advance and go to crush UTME questions? The first question: the energy contained in a wire when it is extended by 0.02 meter by a force of 500 Newton is? So let's write the data. So from this question, we are looking for the energy contained in a wire that is extended. Remember, we said that kind of energy is called the elastic potential energy. So let's write down our data. Our extension is 0.02 meter. Our force is 500 Newton. We are looking for our elastic potential energy. So we have E, F, and little e. So this is the formula that best suits our data. So elastic potential energy is equals to 1/2 Fe. Simple, let's substitute our data. 1/2, our F is 500 and our extension is 0.02. So our answer will give us our 5 joules. So our answer is what? A. To the next question. A spring of length 25 cm is extended to 30 cm by a load of 150 Newton attached to one of its ends. What is the energy stored in the spring? Energy stored in the spring, elastic potential energy. So let's write down our data. A spring of length 25 cm, this is our initial length, L1, 25 cm. Is extended to 30 cm, that is our final length is 30 cm by a load of 150 Newton. Please don't confuse the word load. Load simply means it's still force. Force of 150 Newton. Calculate the elastic potential energy. So now, please take note. From these two data here, you can get your extension. Remember, extension is equal to our final length minus our original length. It's final length minus original length. The original length of the material, then after you stretched it, that's the final length. So the difference between the both lengths will give you an extension. So that's 30 minus 25, which will give you 5 centimeters. But please take note, the SI unit for length is not centimeter. So we need to convert the centimeter back to meter. Always take note. So converting centimeter to meter, you divide it by 100. If you are converting from a small unit to a bigger unit, you divide by the conversion rate. And if you are converting from a bigger unit to a smaller unit, you multiply by that conversion rate. So the conversion rate between centimeter and meter is 100 because of cent means 100. So you divide it by 100 and it will give you a 0.05 meter. So now our data is F, extension, and elastic potential energy. That's this. So our elastic potential energy is equal to 1/2 Fe. Our F is 150 our extension is 0.05. So it will give you a 3.75 joules. So our answer is 3.75 joules. That's C. To the next question. A spring of force constant 1500 Newton per meter is acted upon by a force of 75 Newton. Calculate the potential energy stored in the spring. Don't forget potential energy, that's our elastic potential energy. So now let's write down our data. Our force constant K is equals to 1500 Newton per meter. Our force is 75 Newton. And we are being asked to calculate the elastic potential energy. So now see, F, EP, and K. There is no formula like that here because of I did not find the derivative. So this one gives us. So look at this. This one is when you are being given force and extension. This one is when you are being given force constant and extension, but there are some cases where you'll be given force and force constant alone without extension. You can get that from Hooke's law here. So we can get our extension from here, then put it back into this formula. So our F is equals to KE. So for us to find our elastic potential energy, we need to get our extension. So we can get it from here. Our force is 75. Our K is 1500 multiplied by E. So divide both sides by the coefficient of E, which is 1500. So our extension gives us 0.05 meter. We will then bring in our formula. Whether we choose to use this or we choose to use this, any of them we use will give us the same answer. So for preference, I choose this one. So our elastic potential energy is equals to 1/2 Fe. 1/2, our F is 75 and our E is 0.05. So it will give us 1.875. So our answer is in one decimal place. So that's 1.9 joules approximately. So our answer is what? A. To the next question. A copper wire was subjected to a tensile stress of 7.7 times 10⁻⁷ Newton per meter square. Calculate the tensile strain of the wire. They give us Young modulus as 1.1 exponential 11 Newton per meter square. So we are finding our tensile strain and we are giving Young modulus. So we are using our formula here. So let's write down our data. Our Young's modulus is 1.1 exponential 11 Newton per meter square. Our stress is 7.7 exponential 7 Newton per meter square. Our strain is what we are looking for. So simple from our formula. Young modulus is equals to stress divided by what? Strain. So let's substitute our data now. Young modulus is 1.1 exponential 11 is equals to stress is 7.7 exponential 7 divided by our strain, which we are looking for. So we can choose to switch these two expressions here. It will not look like this. Strain is equals to 7.7 exponential 7 divided by 1.1 exponential 11. If you choose, you can just cross multiply, then divide both sides. So just to save time. So now our strain. So our strain does not have any unit because of its extension over length. A catapult used to hold a stone of mass 500 grams is extended by 20 centimeters with an applied force F. if the stone leaps with a velocity of 40 meters per second, the value of F is, this is a scenario where the elastic potential energy in a stretched catapult is converted into the kinetic energy of on a propelled stone. So in a case like this, you must relate both energies as rightly stated here. So let's write our data down first. Our mass is 500 grams. We need to convert this to kilogram. So from small to big, you divide it by the conversion rate, which is 1000. So this will give you a 0.5 kg. Our next data, extension, is 20 centimeter. So we need to convert it to meter by dividing it by 100. That will give us a 0.2 meter. We are looking for our force F, and we are given velocity as 40 meters per second. So now, as I said, let's write down our formula. Elastic potential energy in the stretched spring, Fe. Now I am using Fe because we were given F and E, but if we were given K, I would have used Ke squared. They are the same thing. So 1/2 Fe, our elastic potential energy in the stretched spring converted to kinetic energy in the propelled stone, which is 1/2 mv squared. So now remember, half they can cancel out. So our Fe is equals to mv squared. We are looking for our F, so we'll divide both sides by what F is carrying, which is E, by the coefficient of F. So E cancel E. So F is equals to mv squared divided by extension. Now let's substitute our data. So our mass is 0.5. Our velocity is 40 squared. That's 1600 divided by our extension is 0.2. So this will give us 4000 Newton. So our answer is left in standard form. 1, 2, 3. So that's 4 times 10 to the power of 3 Newton. So our answer here is what? B. So let's take the last question. If a force of 50 Newton stretches a wire from 20 meter to 20.01 meter, what is the amount of force required to stretch the same material from 20 meter to 20.05 meter? This is actually a relationship kind of question. Let's write down our data. If a force of 50 newtons, so we have our first force, or there are two forces here, is 50 newtons. And this force stretches a wire from 20 meter to 20.01 meter. So, to save space, our extension, our first extension, is our final length minus our original length. That's 20.01 minus 20. This will give us a 0.01 meter. What is the amount of force required? Our F2 is what we are looking for, to stretch the same material from 20 meter to 20.05 meter. So our second extension now will be our final length, 20.05 minus our initial length, 20. This will give you a 0.05 meter. So now, remember, the relationship between force and extension is a direct relationship. That means as one increases, the other also increases. And as one decreases, the other one decreases. That means our first force is directly proportional to our first extension, and our second force is directly proportional to our second extension. As simple as that. So our first force is 50 newton, Our first extension is 0.01 meter. Our second force is what we are looking for, F2, and our second extension is 0.05 meter. So now what we do is what? Cross multiplication. F2 times 0.01 will give us our 0.01. F2 is equals to 50 Newton times this will give you 2.5. So now we are looking for F. Divide both sides by the coefficient of F2, our final force. So this will give us our F2 is equals to 250 Newton. So our answer is what? C. So, future rockstars, this is basically what you need to know. Do well to master these formulas and always understand the question, what the examiner desires or intends in that question. By that way, you will always arrive at the right answers. If you enjoyed this video, what are you waiting for? Hit the subscribe button and turn on the notification so you can be notified when more videos like this comes. It's my mission to help you cross your high school. So do well to also comment and like the video. In the next class, we will be treating machines. You can't afford to miss that class. And soon, we will be kickstarting our chemistry ignition series. That's why I say, don't wait. Click the subscribe button and follow. I remain your host, Josh White, living to catch you another day. Shalom.